Okay, nice. I'm Andy. I'm the CTO of this company called Bobsled, which we started about 18 months ago. And I know Ali, so he invited me here. And one of the first things I did after deciding I was going to start a startup, at the time I was working at Neo4j, where I was a Java engineer on the clustering team. I had been on the database as a service team. First thing I did was call Ali and say, I'm starting this business and we're going to need to make a SaaS product in the cloud. It's not going to be a Java monolith, and that's all I've done for 5 years. So what are the cool technologies that developers use these days that I need to be using? And he reeled off a great list. He said, you use Vercel and Next.js and Cloudflare and Prisma and a bunch of other things. And I was like, whoa, but like, where do I start? And he's like, well, TypeScript, good starting point, threads. That chimed with my experience going back. So when I was a lot younger, in my first job, I was doing C#, and I remember this Node.js thing came out, and you could suddenly run JavaScript on the server. I was like, well, I spent all my time writing client-side JavaScript and sometimes C#. Like, why can't I just write all the time JavaScript? That was pretty cool. And then a couple of years later, I heard about this thing called TypeScript, and since my boss at the time said, no, this server-side JavaScript thing isn't going to catch on, I'd stay away from that if I were you. Let's just write JavaScript for the browser. A little bit later, I remember when the first version of TypeScript came out, and I went back to my boss, still at the same company, and said, look, we use C#. The same kind of guys have made this TypeScript thing. It seems pretty similar. Wouldn't it be great if we started using TypeScript just on the client side? And he said, well, I'm not sure. I think we should wait till 1.0 and see what happens. So I moved on to a different company, wrote a lot of Java instead. Thought I'd learn some new things. I went to Cupertino, the company that I was acquired. I came back to London after a while. I had a startup where I was the head of engineering, and same transition. So I had been writing Java, went to a company and needed to do something faster, something a bit different. I was like, I'll try Node.js. I think that sounds like fun. Seems to have caught on a bit. But writing JavaScript coming from Java seemed like a bit of a pain. I heard about TypeScript. I tried it. It felt a bit slow. I was under a lot of pressure. So I wrote a load of CoffeeScript. About a year and a half. Any CoffeeScript fans? Yeah. That's pretty much my hiring experience at that company when we raised Series A. And we managed to hire some engineers after raising Series A, and probably about 2 or 3 weeks in, one of the senior engineers I had kind of took me aside, got someone else, said, we need to stage an intervention. We can't keep developing this in CoffeeScript. We need to switch to TypeScript. So at that company, we ported everything to TypeScript. It didn't take us very long. It takes about a week, which is pretty good. We obviously did some of the tricks everyone knows to start with more flexible types and a lot of any everywhere, and then backfill until it was all working nicely. So yeah, when Ali said you need to do this thing in TypeScript, I'd already had that experience before and I thought, okay, let's do this in TypeScript. It seems to work. And now I can hire engineers. It'll be great. So at Bobsled, I said what we're going to do is we're going to use TypeScript, and we're going to be a TypeScript first company. So we're not just going to use TypeScript in the browser. We're not just going to use TypeScript on the server side. We're going to write our infrastructure as code in TypeScript. We're going to write our bash scripts and our deployment scripts in TypeScript, and we're just going to do everything in TypeScript. And that way it will be great. So this is some of the stuff that we've learned and picked up by taking that approach. And I'm pretty proud that what we have is in our repository is almost exclusively TypeScript. There's a tiny bit of Terraform and there's a tiny bit of bash, but we are TypeScript first. So TypeScript first, we have used strict and all the types on everywhere. We dislike any as much as probably most of the rest of you. So these are some of the examples of places where we have had to come up with some tricks to do end-to-end type safety. So browser to server or client server communications. I'm sure people are familiar with TypeScript, may have seen drama related to whether or not you should type things between the browser and the client, controversy around DTOs that Alistair mentioned. That's one of the areas, right? We've got to go from the untrusted browser to the server, and we wanted to have type safety there, so I'll talk about that. Another place is reading and writing to the database. We use Firebase. It happens, let's say, Ali told me to look at Prisma and look at PlanetScale, look at a bunch of things. I ended up coming back to Firebase in our application, but I've worked on a couple of database startups, Neo4j, and another earlier startup on top of Cassandra. So I've used a few databases and know about this problem of, we've written something to the database, we want to pull it out again. how do we get types attached to it? Then one of my more ambitious projects, right, is getting from deployment time to server runtime. So we use something called CDKTF, which is a TypeScript wrapper for Terraform, and that lets us write our Terraform definitions of our infrastructure. So storage buckets, projects, IAM permissions, serverless functions, all those kind of things for AWS, Azure, Cloudflare, Google Cloud. We can write those in TypeScript using CDKTF. We wanted to go a little bit further because we realized that at runtime we need to know lots of these properties that we set at deployment time. And often you'll play around with environment variables in Bash, right? Like, oh, when I deploy to this environment, I set, Google Cloud Storage URL, all caps in an environment variable file somewhere, and if I go somewhere else, I change the values. Most places I've worked have built up a sort of craft of these environment variables and things we pass in, and then we start writing config files somewhere and shipping those around. But I wanted to say, when we need to know at runtime what's the address of this thing, or what identity should I be using, or things like that come from deployment time, let's make that all type safe as well. I'll show you how we do that. And then the other place we have end-to-end type safety, I've sort of put server to Lambda. Right? So we actually use Google Cloud serverless functions, but Lambda's shorter and fitted in more nicely on the slide, and we do use those as well. There's lots of cases where we want to use serverless functions these days. So we have pub sub queues and then functions that consume off of pub sub queues. We have functions that call other functions directly in a kind of REST microservices style as well. Lots of cases where you want to have functions and other functions triggering each other in the cloud, and those are not running the same process, and there's some data transfer happening between them. I'll talk about how we make those type safe and kind of wrap some types so that we can call a function that might be executed somewhere else, or put something onto a queue and pull it off again, and keep types on those. So first up, we do server to document database. This is why my talk had to come after Ali's, because we use Zod for this. It's a nice example of Zod. Whenever we read or write to the database, right, before we write in our data access layer, we actually check. This is being a little paranoid, but it's nice to be sure that your database contains what you expect it to contain. So in our data access layer, we have methods to write, and they actually parse with Zod before they write to the database, particularly because Firebase is a sort of NoSQL, very flexible document database. This helps us avoid extra cruft appearing, right? And as Ali showed in his example with the sort of is success true, one of the advantages of parsing is we strip off any extra properties that might have accumulated onto objects in our code, and we get exactly what we expect in the database. Reading, right, when we read out the database, we also parse, and that means we get early failure if something really bad is happening. So, if unexpected data is in the database, it fails pretty much immediately on read rather than somewhere deeper in the code that's more confusing and harder to debug. And because of the first point, the second point almost never happens, which is good, but occasionally solutions engineers, or more often me, go into the database and try and fix things manually, and this catches when that's happened. To do this, the main tip is create a data access layer, and I'll show a quick example of that. But this works for all kinds of stuff that I mentioned, right? If you're writing data to storage, if you're writing stuff to files in the file system, if you're dealing with untyped APIs, Zod is really great for all of these cases. Now, I'm not as slick as Ali when it comes to this, but here's an example of how we do this. Don't think we need a terminal at the moment. Okay, hopefully it's fairly reasonable. This is an example I pulled straight out of our code pretty much, of a schema in Zod, all the usual stuff. So here we've got our Zod types, right? Z string, Zod array, Zod other string, and then we use infer, like Ali showed, to actually get the runtime types. Right? We've got enums in here, which we use in a few places. We've got the status, and then we've got this actual object, which this code doesn't expand. So we define the type. Then we define our write and read methods. So here, for this flag type, we've got a method to create it, which is not actually parsing in this example. It's a bit naughty. We should. So we should be doing in here flag schema parse. There we go. Right, so now we've parsed the data before writing it into a database. So set doc is the actual command to write into Firebase. So we expect to get flag, and then this thing we're parsing according to the schema, even though it should be obviously here, but we have more complicated methods where it's needed. Then we write a read method. There's some caching and other exciting stuff going on here. We have implemented this method, which gets parsed documents, but doesn't return failures. So we use this where we're reading from collections, and there might be a few items in the collection that don't parse. And what we want to do is show the user everything that parses, and then throw an error and send some alerts to Slack to say there are some documents in here that don't parse, rather than just crashing if there's one document in 100 that's in some way corrupted. So when we're doing read, we put it through this method, we pass this method the schema and the path to the collection, and everything that's read out of this is everything that parses correctly. And we use that safe parse method that Ali showed briefly, which tells you if something parsed or not, rather than throwing an error. Do that. So that's how we do, in and out of the database. Nice usage of Zod. Browser server. This is more interesting because we don't trust the browser, right? We can't rely on the browser to send us what we're expecting, and that's going to get interesting. But we can trust the server to send the right things to the client. And we use Remix as our sort of framework. It's a server client framework for writing React and hosting and serving React. We actually, on the subject of open source, we maintain a Google Cloud Functions adapter that allows you to run Remix in Google Cloud Functions, which is open source, and we're looking for other people who want to help, if anyone wants to help with that. But anyway, we trust the server to send the right things, but it's quite nice if we can have strong types on the client side. And Colin, who's also the author of Zod, was instrumental in getting a pull request and a change into Remix that allows us to have strong types between the client and the server in Remix. So here you see we've got a loader. That's essentially what happens in the Remix framework when you do a GET request. The loader executes on the server side, and the loader returns, whatever the loader returns ends up on the client. So here we've got a very simple type. We use this JSON, which is part of the Remix framework, to send this back. Then in here, when we do get data, we use this loader data tool, which is part of the Remix framework, and we give it this type of loader, and the type that we get there is correctly typed by the magic of generics. So this is that. Here we have this loader type. When we do type of loader, what we get back here has the same type that we returned from this function, and we can add something else in here. I should let Copilot do that, and now we see we've got our hello in there. Make it const. Right, so hello is nicely typed, and we can, do our get data just to check. There we go. Looks good. VS Code says it's good. So there we've got immediately, out of the box, nice types for data that we return on get from Remix. The same is true of things that we get back from a post. So when you send a post request to the server, after it's processed it, it sends you some response. In Remix land, that's action, and what you get back from an action can be typed using use action data. And we've got a nice type on here. This is a slightly more complicated type. It includes, unions and other stuff happening. But this gives us, strong types between the browser and the server straightforwardly and nicely. And this is from our website. So there is a hopefully working localhost is working, and this is from our website. So if you want to know more about Bobsled, you can ask for the white paper. It's somewhat corporate. And this has a form. So we can show an example of how this actually works a little bit in practice using this form, just to prove there's something happening. If I put in my iCloud email address and submit this form, we get back an error saying, please use company email address. This is dealing with data that's been posted. Right. So this is client side, we're posting data to server. This form gets sent into form data. How do we deal with typings on this? Right. We said we don't trust, so we use Zod for this part. What we do on the server is we receive this form data. Right, this is a normal Node web standard form data object. This is a normal Node request object. And we can parse that with this ZFD form data. What ZFD form data is Zod form data, the library that works alongside Zod, basically helps you take form data, which is a slightly funny data structure, and parse it with Zod schemas. So we're passing a regular Zod schema here, which looks like this. And this is a little bit complicated. This is a discriminated union. This is kind of advanced Zod, but it's a type that lets you choose between two different types depending on a particular property. The property here is intent. We use this because there are multiple form submissions possible on this page. So on this page, you could ask for us to call a function, or you could ask us to share the white paper. There's two different things, and those, depending on which form you submit, we get different data. So if you ask us to share the white paper, you get the contact form fields, and I am not as good at VS Code. There we go, it's Ali. But this is our Zod form data type for the form field. So first name, last name, email, and company, right? That's what we're going to submit in here. And if we post something that isn't that, we'll get a parse error, and we'll send an error back to the user here, right? So if safe parse is not successful, then we can immediately return error. Hopefully that doesn't happen, but if someone malicious is posting things to our server, we'll catch this. And then if someone actually posts the correct thing, we have a switch statement to figure out which thing they sent us, and this form data then is typing is unpacked because of the magic of discriminated unions, and this is strongly typed, right? Because we've parsed it with Zod, and we can send that into the functions that we're going to execute. And yeah, if I don't put a company in here, so I can put Andy at Bobsled. If I don't put a company, it says please enter a company name. We're able to hang that off some of the capabilities of Zod as well. I'm not going to go into that too much, but we can parse those form properties and come up with custom errors based on each of them. Going back to this. So yeah, we use Remix for the magic of server to client typing, and then we use Zod and Zod form data to give ourselves typing when it's coming from the client to the server. Now, this is where things start to get a little bit interesting, is we want to have types between our deployment time activities and our runtime activities. So first of all, a huge shout out to CDKTF. This allows us to write our infrastructure as code, which you may have done with things like Chef or CloudFormation, or I'm trying to think of other technologies are. There are a few other things out there. Kubernetes is probably an example, I think a lot. If you use Kubernetes, written a lot of YAML. So there's a bunch of technologies for writing infrastructure code. Terraform is one of them. It's very good. It comes from HashiCorp. And CDKTF is a wrapper to generate Terraform programs using TypeScript. So this looks like this. So we make a stack, and these types are straight up Terraform types here. Don't worry too much about providers. But here we're going and just creating a Google Firebase project. So I just say with this type, I want a Firebase project. I set some properties. This is straight CDKTF. Pretty straightforward. And now I've got this Firebase project. When I execute Terraform against this, it will create a Firebase project in Google Cloud for me. So I've got a database. It's a good start to having a full stack SaaS application. Then there's some other stuff I can do in here, skipping over a little bit, but say I want to make a Google storage bucket. I just define that like this, give it a name. So there's a Google storage bucket with this name. When I run Terraform, that Google storage bucket will be created. I'm actually going to put an object in that bucket, which is the code we're going to run. And we'll create a cloud function using the object in that bucket and Zod Terraform. So we can define the infrastructure that we want to have. In TypeScript, all of these types are strong. So if I start doing weird things like putting the wrong types in here, I'll get nice compile time errors. Maybe not on that one. Right, if I forget to name this function, it doesn't compile. So that's a good sign that we've done all the things right. And yeah, so we can deploy a whole load of infrastructure by writing this CDKTF and then executing CDKTF runtime, which will deploy it. Now, trying to say, why do I then care about having this available? So this is nice, this is strongly typed. The next step is I want some of this information or some of the outputs of this available at runtime. So I've just created this cloud function. What I want to do from my web app is call this cloud function. Right? It's kind of common microservices pattern. In order to call this cloud function, I need to know its URL. And that's an output property of Terraform. So I do this cloud function. Somewhere buried inside here, service config. Right, there's a URI. So this isn't known until after it's been deployed. I might be able to write some complicated string templating to assemble and guess at it. They might follow some rules, but really it's much better for me to say, let's take the output from what gets generated. So this will be populated when Terraform is executed with the output of the URI, which is where Google has decided this function is going to be. And it's going to have some UUID and some other stuff in it that won't be known until deployment. And I want to know this in my app at runtime so I can call this function. So how do we do that, and how do we sort of plumb that through in a way that is nice and strongly typed? What we do is we generate this other stack. Terraform is made up of stacks, which is an output stack, which is slightly complicated here, but what we're going to do is we're going to write some JSON, and we're going to write some JSON using Zod, so that we're pretty confident that it has the expected type. And then at the end of our deployment, that JSON is going to have the type we expect that contains some properties which we want to know at runtime. And we type this. We've actually got this stack output. This is our own class. I think it might be as well. See? Yeah, it's our own class. Does something with generics. And we set the type that we're going to output here. Digging another nice Zod schema. And here, these are all of the properties that we emit at the end of our deployment. And then everything that's set on here, we can make accessible at runtime. And we do that by writing that JSON file, shipping that JSON file, and then at runtime, we can read it, parse it again with Zod, and have access to it strongly typed. So I have a bit of a wrapper around the code that does that reading. But anything I want to know at runtime can be declared on here. I know it's going to be written. It's going to be parsed by Zod before it's written during deployment. And then I can read it out at runtime. So if I want to call a function, that's not the one, sorry. Here's an example. So we have this function, get environment, and this gets our Bobsled environment, and that's the type that I was just showing you with all the deploy time properties, and then we can use the environment, Bobsled environment, to get some things like the function URL. Right, so this example function URL will be the outputted URL of the function that we just declared with Terraform. And we can then call that URL, with fetch. We actually have a slightly more complicated way of doing it here, but if I wanted to, I could just call that URL with fetch, and things would all work. So that's how we get from deploy time to runtime with a lot of type safety and confidence. And there's lots of things you can use it for, right? So common examples for that: addresses for functions, database connection strings. We use this for sending our Firebase configuration to the client, because Firebase can be called from client side as well, but it generates a unique configuration in each environment. So we can automatically wire that up. Addresses for cloud storage, storage buckets. Another thing we use it for a lot is identity to impersonate. So we do a lot of cloud infrastructure management, and we often have to impersonate identities from different clouds. So keeping track of which AWS identity should I be picking up, or which Microsoft Azure identity should I be using for something at a particular time is a pain for us. And we're able to do all that with these nice strong types. One of the other things that we do around this is we actually build for an environment. So some of this stuff happens during our build time. So we set which environment we're working with, we build, and some things get baked in at build time, like this output JSON, and then what we ship has been baked for a particular environment. So another thing we do this kind of communication, right, is from a server to a Lambda. So we just deployed a cloud function. Now we want to call it, and that function itself has arguments and a return type, and we want those to be strongly typed. So how do we get all of that to work? So we use the address, right, to talk to the function that we got from our deployment. We actually use a service account. In this example, you can see there's a service account to impersonate, which is also being set. So when we call the functions, here they're secure, and so you can't just call it by calling the URI. You actually have to do some authentication. This is wrapping, this invoker GCP function is wrapping that authentication and using this impersonation. Here we mostly trust ourselves, so we don't necessarily need to do Zod parsing for arguments that get sent to our own cloud functions and the stuff that gets returned from them. But we still want to have nice types, so we can do this using generics. We don't have to necessarily go into Zod. So when we call this function, we've got our own wrapper here called invoke GCP function, and it takes as a generic type parameter the implementation of the function that we're calling. So if I go to hello world function, get this. So this is the function that I've written and slightly adapted from our production code. And here we just return a type, right? Hello world, it's got time, which is going to be inferred as a number, and magic. Notice here, there's no return type set. So we're making use of type inference, one of my favorite features of TypeScript. We have, in this case, got a Zod type on the arguments that we're passing to the function. This is kind of overkill, but we do it in some places because it makes us feel better, and it's not particularly expensive. So this is actually a Zod typed call. So this function is also written in the code base. When we did the deployment, we have a nice trick going back to the output stack where, not the output stack, the conductor stack. The code that we shipped is from node modules. So our infrastructure as code is an npm package, right? So I have a package that deploys infrastructure. That package has a dependency on another package in our monorepo, which has the implementation of the function in it. And then when we do npm install, that becomes accessible on the node modules path. And when we deploy, we take this thing and we stick it in this Terraform asset, and we use that asset to build a zip of the package. So this is all within our monorepo. We've basically just written this code to say we're going to grab that node module package, zip it up, and ship it to Google Cloud. Google Cloud functions, one of the ways you can set them up is with a zip of an npm package. This means that our monorepo build knows that there is a dependency between this infrastructure as code package and that implementation of the function package, because they're expressed as node dependencies. We use something called turbo repo in our monorepo to build, and because this dependency is tracked by npm, turbo repo can know when it needs to rebuild the infrastructure or not, because we've changed the function code. So not so much about type safety, but a nice thing that we can do there. So we trust ourselves to do all of these things, and we've got this function that we've written. We've shipped it into Google Cloud, and now we want to call it and get the return type with strong types. So hello world has been passed on server as the generic type to this. Our generic typing, Ali is probably going to tell me, is much more painful than it needs to be, but we take this function, which is written with this extends, and wraps this other generic parameter out, which is the return type of the function, and then we say that to call this wrapper method, you have to do invoke params, right? Pulls the payload t, which is the arguments type that we pulled off of the function using generics, and it returns the async return type of the function. So we use generics to unpack this function, and the results that we get when we do this is that if we don't use the right parameters, for example, this won't compile. Right. It says this is not assignable to type. So magic. Now it should compile. Excellent. There's also, you might have noticed in here, there's a constraint check that we put on that says this must be assignable to JSON. So you can't sneak any dates or other things in here because we are going to serialize this and we are going to send it over the wire. And if you try to do something like serialize a date and deserialize it without doing a bit of extra work, it doesn't work. So we've constrained the types that can be sent in this payload as well. So you can't make this work with a function that won't do the data transfer nicely. So we've got strong types there, and the return type has got the return type of our function. So when this runs, it's going to send the call across the wire using fetch and all that stuff. But what we end up with is a nice strongly typed object. And if we change the signature on hello world to return something different, so hello London, actually it's not going to work. Change the property. London. Hello. We should see that this result type now has London rather than hello in the properties. Right, so VS Code has nicely magically tracked all of that for us. I'm going to put this back, otherwise I'm going to get yelled at by ESLint. And on that. So now I've got two things to try. I'm even more of a cowboy than Ali, so I was finishing this up during the first talk, but I'm going to try for a live demo, and we can go through some different steps in terms of live demoing. So first of all, I'm just going to sort of try and prove that all of this works and go to our careers page. So this is the local copy of the website. Go to the careers page, help us share the world's data. Open positions, we've got more positions now. I didn't quite get that done during the talks, but we are hiring for other kinds of software engineer and SRE. I've added this button down here. It says TypeScript demo. And going back into our remix, here's the action that's going to be called when I hit that button. This is going to call the example function and then wrap the results back to us. So this thing we're just looking at with the GCP invoker and all that other good stuff. So this is going to run remix locally on my machine, but it's then going to call out to the function that I've deployed and send something back. And the function we deployed was this thing. So it's going to say hello world and some time. And it's going to take a little while because this is using Google Cloud Functions and they do use containers, unlike Cloudflare, and so they have cold start. But there we go. So there's potentially premature. One thing I was going to try is we're going to see if we can change this, deploy the function, run the code, and see the change. So we change it to London. Hello. I can bring back my terminal. I'm really bad at using VS Code. There we go. So we're going to deploy, pm deploy environment. Okay, so this is Turbo Repo. So the script is first building everything with Turbo Repo because we've changed the dependency. Right, we made a change in Hello World. I probably could have demoed it showing full Turbo before making a change, but I was a bit late for that. So this is first building all the packages. Synthesizing is creating the Terraform. So the Terraform process has kind of two steps. At first, we run JavaScript, right, a Node.js program that takes all that JS we wrote. That outputs a rather scary JSON file, which is a Terraform program. And then the Terraform program is executed, and Terraform itself is written in Go, and it's binary that's shipped. So that Terraform program executes, and that actually creates the cloud resources. So this is Terraform executing the program that we generated from TypeScript. There's lots of happy messages. There's all kinds of stuff happening here because I pulled this out of our main code. So it's checking to see if there's a Firebase database and all kinds of other things that aren't that relevant to the demo going on here. But the nice thing about Terraform is it only makes changes it needs to. So it skips through quite a lot of these because I've already run it once. But we see here, it's told us that it's going to make some changes to this Google Storage Bucket object. This object is the zip file with our npm package, our runtime function. That changed because we changed the source code. So it says, hey, this thing's changed. I'm going to deploy a new zip file. It's going to do some Firebase rules because they need a fix. And then it says this function is going to be updated. This Google Cloud function is going to be updated in place to point at this new zip file, which is the new implementation. Now, Google Cloud Functions are not as good as Cloudflare, so they also take a little while. I'm a huge fan of Cloudflare. I wish we could use it more. I look forward to us getting onto delivering data into Cloudflare R2. But yeah, at the moment, we're mostly in Google Cloud. So while this builds a container and does some very old-fashioned stuff like that, in order to deploy a function, I'm just gonna riff a little bit. Okay, so we got through that. Lots of other Terraform happened. If we go into Cloud Functions, you can see there's some things spinning because stuff is happening. This was deployed at 20 past 5 last, showing that I was prepared before the start of the meeting with something that worked from the Starbucks, just the other side of the street. And yeah, that's finished. We got a nice full turbo because we do a double check at the end. If I refresh this, it should show, there we go, 7:55. So we deployed our function. Now I can run my local, go back to my local careers page, right? Open positions. And when I hit the button, hopefully we're going to see London hello instead of hello world. Wait, one second. I probably need to restart this because I changed types. Fingers crossed. And otherwise, think of this. See? There we go, London hello. Great, and that is the talk. Any questions?
Thank you very much for that, Andy. Any questions from the audience? Okay, to make it easy on me, you're going to be first.
Hi, yeah, I've just started digging into the TypeScript CDK for Terraform recently as well, so that was really interesting. I'm just wondering where your remix build process fits into that. Does that come sort of last in the process after all the Terraform configuration?
Yes, so the way that we do it is we build and deploy what we call the environment, which is kind of all of the infrastructure, and then we build our applications and ship our applications when we do this real. So I kind of packed all of that into one stack for this demo, but normally we kind of build and deploy the environment, then we deploy functions into that. And for us, the Remix app is deployed as a function, a Google Cloud function, but we do it after we've sort of provisioned the underlying infrastructure, then we deploy individual components. That also means we can manage different versions and things like that.
If I can just follow up.
Yeah.
So the outputs that are coming out of your Terraform configuration, are they baked in at build time into your remix?
Yeah.
Yeah.
So for us, for most things, we can just bake them in a remix in a build time. There are situations where you can create like a circular dependency, where that becomes a bit more tricky. And what we don't do that because we don't need to. But where I've experimented with it, what we've done is ship the JSON into Google Cloud Storage, and that means you can read it out and have sort of circular dependencies. So you can deploy everything without baking in at build time, and then right at the end of the process, collect together all the information you want, put that into Google Cloud Storage in a like canonical location, and then pull it in, and it's typed and parsed and so on.
All right.
Hi, really cool stuff, and the smoothest transition into a hiring page in a full code. If tomorrow we all go into our work and pitch to our CTOs to go TypeScript first or TypeScript only, what's the best thing about it, and also conversely the worst or most painful thing about it?
And the best thing about it is that you can work on any part of the code, and so if you need to implement a feature that touches different things, right, requires a bit of infrastructure, requires a bit of front-end work, requires a bit of back-end or a pub sub queue or anything else like that. It's very easy for one person to work through all of that without kind of context switching or needing to find someone who's an expert in a different programming language. The other thing that's really good about it is because we touch everywhere, we don't have to have any kind of intermediate language things going on, right? So we heard about protobuf and Cap'n Proto. Cap'n Proto is extremely cool. I looked at it a lot when I was starting, but we don't need any of that, or GraphQL, or Swagger, or all those technologies that exist to help you have kind of shared types between different programming languages. So we don't need any of those things. We just write our types in TypeScript and use them. It means that we can develop very fast. The worst thing about it, the NPM ecosystem is a bit of a security risk in some ways. One of the things that keeps me up at night sometimes is thinking about NPM security. So that might be something that your CTO or CSO raises if you start talking about TypeScript and Node being everywhere. Otherwise, the usual pushback is around using the best tool for the job. There was definitely a big trend in software engineering sort of 5 years ago to say, everyone would say, we use the best tools for the job. We use R for this and Go for this and Rust for that other thing and Java for this. And there are good reasons for doing that. And the thing we have is we don't always have the best tool for the job. Sometimes we just make it work in TypeScript, even though it would be better to do it using R or Rust or something else.
All right. Any other questions?
Thanks for the talk. I've got two questions. First one is, having used Terraform a lot, things can get quite slow quite quickly, like the more you use it, and it seems like you, in your setup, it's woven into like the core of your deployment for your application and your functions and your web pages. I'm curious as to what effect that's had on your team and whether you've had to spend a lot of time thinking about this or improving that.
Yeah.
Second, maybe answer that one first.
Yeah, I'll forget otherwise. Yes, it's a really good point. We quite deliberately make use of lots of small stacks. So that is a big kind of challenge you can run into with Terraform is you get large stacks that do lots of stuff and they become slow. Even with all this clever stuff that Terraform does around checking what it needs to update and everything else. So one thing is, because we can wire it together sort of nicely using TypeScript and JavaScript, we can manage the complexity, which might be harder to manage if you were using sort of native Terraform and calling it with Bash, of having lots and lots of stacks that do relatively small amounts. So in Terraform, a stack is like the thing you deploy as a stack. So when I did the deploy there, it actually deployed about 5 stacks rather than one big stack. And then we can manage where those get run. So we kind of think of them as like micro stacks, like microservices, where they have a small scope. And CDKTF lets you take the outputs of one stack and use them as inputs to other stacks in a way that's very straightforward. So you can wire up, and then when you run the CDKTF kind of binary run executor, it executes those stacks, but makes sure that it can take the output from one and pass it as the input to the other. But it's not building this huge dependency graph in Go and doing all of it. It's actually sort of coming out and just saying, I just take these 2 strings and pass them over to this other one.
Refactored something in the TypeScript, or you produce an abstraction, and then it complicates the Terraform world a bit. And if so, is that a problem you'd like to work around? Or?
Yeah. So I think it's a really good question about Terraform. Probably for a lot of people who aren't familiar with Terraform, it may not be clear what's going on. But if I show this stack, for example, this is a problem that we run into. So when I make my Firebase project, actually a better example would be my storage object. Okay, so this storage bucket object has a name here called build. This is where we send up our zip file to Cloud Functions. That's the code that's going to be executed. This sort of string that's just loitering here, looking reasonably innocent, ends up as the name in Terraform. If I change the name of this, when I redeploy, Terraform thinks that what I've done is asked it to delete the previous entity and make a new one that's otherwise exactly the same but has a new name. If there are then dependencies on that object, all of those dependencies will get sort of deleted and rebuilt or updated and various things. And it's very easy to come into the TypeScript and start refactoring and being like, oh, I see we've got this called in a couple of places, right? I'm going to do a new function in here where it's like create Firebase, and I'm going to move that into a light. That was fun. Thanks, Copilot. So I move this into a function that's called kind of create Firebase, and in that function where I've like wrapped together some nice things, I've changed this to like the build, or it's like now a parameter to get passed in. A nice thing about this being in TypeScript is that you can do that. So we can kind of construct our own calls in TypeScript that bundle together a few different Terraform components that work together. For example, this thing of saying like a cloud function has to have some source code and a identity that it executes as, and that needs a bucket object things. We actually have that bundled into a single class, and we can just instantiate one of those and pass a few parameters. But when we do those kind of refactors, we cause this exact thing where the Terraform state suddenly is like, whoa, I have no idea what you did there. I'm going to start deleting everything and rebuilding it. And that can be slow. It can also sometimes be something that needs manual fixing, because the cloud then starts kicking in and being like, you can't delete those things like in that order. That's not okay. So we do have to be careful about refactoring. And we've become fairly disciplined about trying to get these things kind of right first time. So you do have to be aware of what part of the code you're working on, right? The front end of the Remix app can be sort of iterated on very rapidly, and if you make a mistake, it's not a huge deal. The Terraform gets executed and written into Terraform state that is long-lived, and if your Terraform state gets too mismatched with your Terraform program, then yeah, that can be a lot of work to unpick.
Right. Thank you very much, Andy. That was pretty much all I had time for today in terms of sessions. Alistair, closing words?
Yeah.
So,